Welcome to this explainer. Let's just dive right in and explore the really fascinating journey of how we actually teach machines to see the world around them. For years, computer vision felt a bit like science fiction. But today, it's powering everything from the facial recognition on your phone to autonomous vehicles navigating city streets. But here's the thing. There's a massive, massive gap between a camera simply capturing an image and an AI actually understanding what that image contains. So today we're going to unpack exactly how that gap gets bridged, moving all the way from raw, meaningless data up to deep semantic intelligence.
Because the ultimate challenge in computer vision is translating those dumb raw pixels into smart, meaningful concepts. To a machine, a beautiful photograph of a dog running in a park isn't a dog, and it certainly isn't a park. It is literally just a giant grid of numbers representing light intensity. So how do we get a machine to look at that grid of numbers and confidently say, oh hey, that's a golden retriever? Well, that translation process is the entire foundation of modern AI vision.
So that brings us to part one. What exactly is representation learning? To really understand how AI sees, we first have to define the core theoretical goal of this whole process.
Okay, the absolute crucial point here is this simple formula. We want to take raw data, let's just call it X, and use an encoder, our F, to map it into a clean, optimized abstraction. And that prize at the end? That's Z, the representation. Think of the encoder as the mathematical brain, or the neural network that's doing all the heavy lifting. The representation is this brilliant abstraction that captures the actual meaning of the data. It strips away all the background noise so the machine can finally make sense of it. Honestly, the better the representation, the better the AI. It's that simple.
But how does it get there? Well, if the machine learns this representation through optimization, which essentially means it uses an objective, what we call a loss function, to trial and error its way to a perfect encoder. You don't just magically boot up and get a great encoder, right? You have to design an objective for the machine to hit. When the machine guesses wrong, it calculates its loss, basically asking, how far off was I from the right answer? Through thousands, even millions of repetitions, it optimizes its internal pathways just to minimize that loss. So representation learning is entirely about designing the right encoder and the absolute perfect objective for it to practice against.
Moving right along to part two, let's talk about the hierarchy of sight and map out exactly what progress looks like as an AI gets smarter. Think of this like climbing a ladder. We start at the bottom with zero context pixel intensity, move up to recognizing geometric textures in feature space, and finally, we reach our ultimate goal, the semantic space, where the AI truly understands object clusters. In step one, pixel space, there's absolutely zero semantic meaning. It's just raw grid values. But as the AI optimizes, it climbs to step two, feature space. Here, it starts embedding local patterns. It notices an edge here, a texture there, maybe a geometric shape forming. And finally, at step three, we hit the semantic space. This is where the magic happens. Semantically similar objects, like different breeds of dogs, start clustering together in the machine's mind. Reaching this third level, that is the absolute gold standard of computer vision.
All right, welcome to part three, the supervised pre-training workflow. So how do we actually force an AI to reach that highly coveted semantic space today?
Well, currently, we do it by brute force. We train deep neural network backbones on the massive ImageNet dataset, which contains 1.2 million labeled images spread across 1,000 different classes. Just pause and think about that scale for a second. Human beings actually sat down, manually scrutinized, and labeled over 1 million individual images, just so a machine could use cross-entropy loss to practice guessing and correcting itself over and over again. It's wild.
By shoving all those millions of images through this layered extraction workflow, the AI builds incredibly powerful generalized features. And these can be used for everything from depth estimation to object recognition. The input image goes in, it passes through these deep convolutional networks or vision transformers, and it extracts features layer by layer until it finally classifies the image. Because it practiced on 1.2 million highly diverse images, these extracted features become incredibly robust. This trained network, what we call the backbone, becomes this amazing foundational tool that we can then use for a massive variety of other tasks.
Which tees up part four perfectly, the power of transfer learning. Because once we have that massive, pre-trained brain, we can adapt it to entirely new challenges.
Now, what's really interesting here is the stark contrast between the sheer volume of that general source task and the highly specialized, data-limited nature of downstream tasks. In the pre-training stage, like we said, we used ImageNet's 1.2 million images to teach the AI basic geometry, textures, and general objects. But what if you want your AI to detect tumors in medical X-rays? Or maybe track crop health from satellite imagery? You definitely don't have a million labeled X-rays sitting around. You might only have a few hundred. Transfer learning allows us to take those general vision skills from the pre-training stage and apply them directly to that downstream target task, even when data is incredibly scarce. The playbook for this is beautifully simple. First, you load the heavy lifting weights from ImageNet, all those layers that already know how to identify basic edges and shapes. Second, you swap out the final output layer, chopping off the classification head that knows about dogs and cats, and you replace it with a new one designed for your target, like predicting healthy versus tumor. Finally, you run your small, specialized dataset through it to fine-tune those final weights. It's essentially like giving a really smart college graduate a specialized crash course rather than trying to build a foundational curriculum from scratch.
But, and it's a big but, this brings us to part 5, the million label bottleneck. This is the massive, expensive roadblock currently throttling the entire computer vision industry.
Relying entirely on supervised learning means we are quite literally bottlenecked by human labor. We simply cannot afford the time or the money to manually curate and label millions of images every single time we want to enter a new domain. The ImageNet approach is undeniably incredible, but it just doesn't scale. If we want AI to deeply understand specialized industrial machinery, rare biological phenomena, or complex environmental changes, we can't wait for humans to label millions of examples first. The cost is absolutely astronomical, and this manual effort is a massive wall blocking the real acceleration of AI.
Which leaves us with this final provocative thought. The entire future of AI depends on unlocking self-supervised intelligence. If we can figure out how to teach machines to look at raw, completely unlabeled data and decipher the semantic structures all on their own, we will unlock an unprecedented level of artificial intelligence. How we design the objectives for a machine to learn without an answer key is, without a doubt, the most exciting challenge in tech right now. So, what do you think? Are we ready to bridge that gap? Because cracking this isn't just the next step for computer vision, it's the gateway to true artificial intelligence.